I'm Xiangpeng Hao from UW Madison. I'm fifth year PhD student working on database and storage systems, and I co-created the Liquid Cache project. So it's, in a nutshell, it's basically a cache, which people put data into the cache and later will efficiently reach the data from the cache. And the Liquid Cache is different from other cache that it will try to understand the data inside the cache. So basically, if you take a Redis, it's just a byte array, right? So, but for Liquid Cache, we understand the data people put into the cache, so we can optimize it, we can better scale up, scale down. So one of the things we found in Liquid Cache is that people put a lot of string data into the Liquid Cache. So we think, yeah, it's probably better for us to do a more systematic study of strings and how can we organize strings and manage string data more efficient. So that's come to this talk on the nature of strings. So Liquid Cache has a lot of different aspects. So I can keep talking about it for like 5 years during my entire PhD. But this is really a zoom in into a very specific and very important part of the Liquid Cache. So how we handle strings. And yeah, my PhD is you can probably find the description is by Influx, but it's actually, I'm not affiliated with Influx, but Influx Data actually funded my PhD along with other companies like Ballplans, BioDB, and the taxpayers of Wisconsin and the federal government. So it's very important we have fundings for research. Okay. Yeah, so without further ado, let's talk about the nature of strings. So we start with a public BI dataset. It's a dataset from Tableau. So it consists of a real-world business intelligence data. For example, people often ask questions about how many users abandon their shopping cart after some time. Queries like this. Okay, so those are business intelligence, so they are real data. So basically, we analyzed the 46 largest data on the Tableau dataset, and which consists of more than 700 SQL queries. So we not only study how data is being stored, but also how data is being read in a SQL queries. And the total dataset is 386 gigabytes uncompressed, so it's pretty large. And the first takeaway we found is string is actually the most important data type, not surprisingly. And we found specifically 61% of the bytes stored in the dataset are string data. So that is larger than all other data types combined. And we also study how many columns being read mentioned in the SQL queries. Right, so the SQL projection here means if we select some columns from the table, then we find that 40% of the columns people select are actually string columns. And considering string columns are usually much larger than, for example, integer columns, then the actual data coming out of the string SQL selection is much larger. And the next, we found that 55% of string columns are read at least once in the dataset. Meaning that, well, for the non-string columns, the number is only 34, meaning that 66% of the non-string columns are never being read in the data set. So string is the most important data type, not only because it occupies the largest amount of the bytes in the data set, but also it's more frequently read than other data types. Okay. But strings are not created equal. So we basically, here's two aspects of strings. We think those are most important two aspects. And on the x-axis is the distinct ratio. So distinct ratio basically measures how many distinct strings in a string column. So for example, if the distinct ratio is 1, meaning that every string in this string column is unique. And on the other hand, if the string distinct ratio is low, meaning that the string column is very repetitive. And on the y-axis is the average length, so it's basically the average length of a string column. And each dot in this figure shows a string column. So we analyze, I think, more than 1,000 string columns, and we plot each of the columns on the figure. So we can see the string columns are like a force in the entire domain space, and there are like short and repetitive string columns. A lot of them are short and repetitive, and there are also long and unique string columns. And of course, there are other string columns in between. So they are a diverse set of strings, even though they are called strings. Then we try to categorize, look deeper into the strings, how people use them, and we categorize them into 4 bytes along the 2 axes. So basically, on the left top is the repetitive but super long strings. Those are like prose, prompts, speech-to-text, human comments, descriptions. Those are natural language strings. Those account for 15% of the strings. And on the left bottom side is the repetitive and the short strings. Those are like genders, weathers, country, states. Those are a lot of string columns like that, but because they are much shorter than other strings, they only account for 37% of the bytes. And on the right top of the region is like a structured input. Basically, we see a lot of people just using like a JSON, XML, URL, just dumps whatever structured data as a string field, and those account for 29% of strings. And lastly, we have the quite short, but also very unique strings like the IDs, hash values, tokens. Those are like not human readable, but meant for machines. So those account for 19% of the strings. And yeah, so we categorize into those 4 types, and why it matters, because even though they all called strings, they're all using strings in the table, they're actually very different. And when in liquid cache, we want to process each of the different type efficiently. So they require special handling. And how? So first we look at the distinct ratio. We can see like more than half of the string are very low distinct ratio, meaning they're very repetitive. For the repetitive strings, here's even more zoom in. So basically, those are 4 string categories, and this is a distinct ratio on x-axis. Y-axis is the cumulative percentage of the string columns. For the categorical data, like countries, genders, those like are almost around like less than 0.1%, less than 10% of the distinct ratio. But for other string types, they tend to have this long tail distinct ratios. So the general principle is if a string column is repetitive, then we want to deduplicate the strings so that we don't have to like repeat those strings all over again. So we call it dictionary encoding. And for the on the other hand, if the all of the strings are unique, then we don't want to have dictionary encoding, just to do it plainly. So we call it plain encoding. Here's an example of the 2 encodings. So on the left-hand side, if it's very repetitive, we do dictionary encoding. Here's an example, multiple strings. There are a lot of repetitions, so we put them into a hash table, deduplicate everything, and keep a key to reference the actual strings in the dictionary. On the other hand, if every string is unique, then this kind of a dictionary is a pure overhead. So we want to have a plain encoding, just concatenate every string one after another. So dictionary encoding is obviously very important for strings because a lot of data are low distinct ratio. It will help us save memory footprint. It will have faster sorting and the comparison, like filtering. For example, if the string has low distinct ratio, we can sort the dictionary instead of sorting the entire strings in string columns. And actually, their systems already have this heuristic. For example, in the Parquet format, what we do is it will always start with a dictionary encoding, keep putting things into a dictionary, and until the dictionary grows too large, it would fall back to plain encodings. So it's kind of like want to strike a balance there's a heuristic there. And the dictionary encoding is not only important for the string storage, it's also important for the string operations. For example, we look at the string encoded data and how they are being processed once read back. Okay, we found that 26% of the string columns, they will run through a filter. If this string is dictionary encoded, then the filter can directly apply on the dictionary codes rather than apply on the entire plain encoded data. And we found that 90% of the string columns will run through a hash aggregation. So if the string column is already highly deduplicated, then we can directly operate on the distinct values. And the rest of the string columns will often go through a projection or selection. For the dictionary encoding, this is very important because let's say if we want to select a string column with every other rows, if the string is plain encoding, then you have to copy every other rows into a new buffer. But for dictionary encoding, you only need to copy the dictionary keys, every other dictionary keys to the new buffer and reuse that dictionary. So it's more efficient for dictionary encoding, it's more efficient for string operations. Okay, so that's the dictionary encodings. And the second axis of the string characteristic is string length. So we found string have very diverse length characteristics. On the left x-axis is the string average length. For the IDs and the categorical data, they kind of stop at this 64 average length bytes. But for the JSON natural language, they kind of this long tail of average length, so they can go super long. And this variable length, diverse set of string lengths will complex storage. So let's review how people store those variable length strings. The first approach is very simple. We just keep a string length followed by the string bytes. So we just repeat this. This is actually what Parquet does. And the advantage of this approach is that it has very high data locality because when you scan the entire string data, you never have to jump between different memory buffers. But also the problem with this approach is it cannot do a random lookup because let's say if you want to look at the 100 string in the arrays, you have to scan through the entire first 100 strings to get the 100 string arrays. And also, one subtle problem with this design is slow UTF-8 validation. For example, for some of the programming language like Rust, it requires all string data to be in a UTF-8 encoded data. So when we read data from Parquet, we can't just say, okay, we can't trust the data to be UTF-8. So we have to do UTF-8 validation. But because in here we represent data in a mix of integer and strings, it will make the UTF-8 frequently break the pipeline of the UTF-8 validation. So making the SIMD optimization very difficult to run. So that's some problems with this designs. And there are other approach like the arrow string array, which is basically have a continuous string buffer and the strings are concatenated one after another. And we have a separate offset arrays, they're integer arrays, and they basically point to the different string locations. So you can do random lookup, and also because you have everything in a single buffer, or because offsets are one next to each other, so the string length can be calculated by calculate the diff between the two offsets. But the problem of this approach is that it requires all the strings into a single buffer. So that, let's say, if you want to select every other rows in the string array, you have to copy every other strings to a new buffer. So that's problematic. And the third approach is in data fusion and the DuckDB's approach. We sometimes call it the German strings. Basically, German string is you allow you to have multiple string buffers. So and also the offset and the offset plus a length, so that it doesn't rely on the next offset to determine the string length. So it can point to any location in the string buffer. So it will allow multiple buffers, reduce the some of the copies when you decode data from the packet. But the problem is also obvious because it will require extra memory overhead. Each string now requires 16 bytes of metadata. So that's some extra overhead to pay. And for strings, long strings, we found that prefix is the most important part of the strings. And there are actually two types of prefix. The first type is those on the left column. Those are pretty distinct prefix, where when you compare two strings, you don't have to read every byte of the strings. Actually, because the first few bytes is enough to determine the string order. So most of the time, we want to inline those first few bytes along with the string metadata, so that we don't have to pay an extra memory jump to read to the string comparison. So that's the first type of prefix. The second type of prefix is, for example, like this in the HTTP URL, where the first few bytes are all the same. So if we inline the first 4 bytes, they are all the same HTTP. So to make it more effective, what we do is we have to do an analysis of the string data, extract the common prefix, so that if we common prefix, so that the compression will improve, also make the prefix inlining more effective. So let's run a real string representation action. So let's say we have some of the strings here, laid one after another. The first component is the string buffer, which we already know is just concatenating the strings one after another. And then we have the string metadata, which help us to point to any string in the buffer. And then we have this shared prefix, which help us to make inline prefix more effective, and sometimes it also helps the compression. And then we have this inline prefix, which, like for example, if we want to compare the first string and the second string here, we don't have to read the entire string to get the compare result. We only need to compare the prefix, the inline prefix. So sometimes the string buffer can be on disk, so that you don't have to load the entire string on disk. And if the entire system is in memory, then you don't have to pay the extra memory jump to a different like cache miss. Right. So that's the string representation in action. The next question is how many bytes to inline? Right. So because we have this intuition that if we only inline very few bytes, then we kind of making the inline prefix less effective, but also we pay less memory overhead to the like metadata. But if we inline more prefix, we pay more memory consumptions, but it's more likely the prefix is going to help us with string predicates. So we did an analysis of the entire data set, basically try to compare how effective is the string prefix. And in this figure shows the x-axis shows the prefix length, basically how many prefix of each string to inline. And the y-axis shows how many percentage of the strings we can distinguish in this string array. For example, if a string prefix is 12 and this is 0.8, means if we inline 12 bytes of the strings into along with the metadata, then just looking at that inline 12 bytes, we can distinguish 80% of the strings of the string array. So here we clearly show that the more we inline, the more we can distinguish more data. And in fact, the real system like Data Fusion and DuckDB will try to inline 4 bytes. And that seems to be a reasonable sweet point here to balance the inline effectiveness and memory overhead. And then we further did analyze over how many bytes are actually used during a string sort. So basically, sort, you have to compare every other strings. Then we analyze a batch of strings, and we found like the intuition is most of the time you only need to read the first few bytes to determine a string order, right? So we quantified this, and on average, only 37% of the bytes are actually being used for a string sort. meaning that if our cache is perfectly designed to cache those 37% of bytes, then we have, during a string sort, we will never have to incur the full string read or full string IO. Okay, and that's a number of string prefix. Next, we talk about compressions. Okay. Long strings have low entropies, so meaning that they need compression. So here are some of the strings we have in real world where like every string is unique here, but they kind of different in a little bit. So it makes the dictionary encoding less effective because every string is unique. Then we have this, we calculate the string compression ratio is 31%, meaning that 100 bytes goes to 31 bytes after the compression, while the overall compression ratio is 66, meaning, yes, confirming that string is more, have lower entropy than other data, meaning that it needs to be more compressed. And there are basically two approaches to compress strings. The first approach is general purpose compressor. So basically, we all know like if we take a byte sequence, feed it to a general purpose compression, then it will output a new compressed byte sequence. And so that works, but it's not optimal. We'll show in the next slides. So the second approach, we call it like string native, string specific compression, which will preserve some of the string semantics of the yes, for the string semantics. So here's a visualization of how it works. Basically, it's very similar. We have some strings, and if we use general purpose compression, we basically will build a symbol table over the strings so that we basically replace some of the symbols to a new output arrays. And if we want to decompress, for example, only the third element in the array, the only way we can do this is to decompress the entire string and then get the third element. But for the FSST compression, string native compression, we will maintain the semantics of the strings so that we know which byte slice correspond to the original string location. So if we want to only decompress this element, we can look at the symbol table and only decompress that one. So that's how people use compression. And FSST is a relatively new algorithm. It's been around like for only 2 years, I think, from CWI research. So that's, we also, in liquid cache, we also use the FSST compression. Okay, so FSST is independently decodable. So yeah, we have basically showed different strings. Although they all called strings, they're actually very different things. And there's one last topic about string is the most common string is null. And we've actually found there are 12% of strings that are nulls. And most of the existing systems have a native ways of handling nulls. But from our study of the real world data sets, almost none of the systems actually use a native proper null. So we call it proper null. So in a proper null representation, every null string only takes 1 bit because it's a bit mask of nulls. But real world, people will try to do stringified nulls. Basically, they just use strings. And sometimes they will just use empties. And it's not just empty, they sometimes have an empty bracket. And if they are from JavaScript, they will use not a number. And we also see like Rust and Python, they also have this stringified nulls. And this makes null handling very challenging because null handling is very important. We found that if the nulls are not handled properly, the data set grows from 196 gigabyte to 308 gigabyte. This is because when a null string appears in the middle of the column, then it essentially forces the entire column to be strings. And usually that takes much longer, that's much longer than like the proper data type. And also sometimes like people use like nulls or nonce, they are pretty long, so they take more than 4 bytes to represent a null. But if a proper null handling, you only need 1 bit. So increase the size. And also sorting, it also makes sorting very problematic. Most of the time we want nulls to appear first or last in the sorted string array. But if the nulls are actually null strings, then you can appear everywhere in the sorted array. So it breaks the null semantics. And lastly, also make unnecessary scan. So in the data scan systems like Parquet, we will use zone map. Basically, let's say we want to find a string, UW Madison, then we look at the minimum string of this column and the max string of this column. If UW Madison is not in this range, then we can skip the entire column of data. But because now it's kind of like a mess around, especially when the empty strings comes in, then all the mean values becomes empty strings. So it will break the zone mapping and also breaks the common prefix, the optimization we mentioned before. So now handling is very important. Finally, we can put everything together. We discussed in Liquid Cache. First, we do null handling. We scan the string data, identify the null strings, and create a bit mask of every string so that it will only take 1 bit. Then with the dictionary encoding, basically have the offset and the length, and so it can jump and the buffer ID so that it will jump into different arbitrary locations in the string buffer. And also we do prefix handling. We run a string to extract the common prefix and then run a 4-byte prefix embed with metadata so that most of the time, if we scan the data, we only need to look at the prefix, don't have to go read the entire string buffer. And lastly, we also do some compressions because some of the buffer is uncompressed, some buffer is compressed, and some buffers are on disk, some buffer are in memory. So we have this pretty convoluted way of handling strings. And yeah, so it's a mix of compressed, uncompressed, in memory, on disk, and different prefix and null handling. And yeah, that concludes my talk on string handling Liquid Cache. Okay. I'm happy to take some questions. Any questions? Okay.
Do I take the microphone? Yeah, take the mic. That is a great talk. I'm a huge fan of this sort of Baker Asterhout style empirical study. And I was just wondering, with your approach in Liquid Cache, were there any sorts of data sets that did not perform as well under these string compression strategies?
We will definitely want to study those data sets, but the purpose of this study is we try to be as comprehensive as possible so that if there are string doesn't perform well in Liquid Cache, we consider it as a bug. So we're going to fix it and try to incorporate those characteristics into our design.
Cool, thank you.
Okay.
So for this implementation, was it like an online cache? Like, do you have to worry about like streaming in data and doing this incrementally and then like evicting data from the cache? Or is this all, you load in one data set and then you build all these indexes?
Yeah, that's a good question. So in our Liquid Cache scenario, we basically position this in like an iceberg kind of scenario where new data comes into the S3 and then it's kind of loaded into the query engine. So, so the short answer is data is already in S3, so we just load it and cache it in Liquid Cache. And they're all in Parquet format, so it's immutable. And if new data comes in, like the way we modify data is we kind of delete those data and have a new version of it. So we just mimic that behavior.
So how likely do you think these like optimizations would work in other languages, like other natural languages? You know, because like English has some properties that maybe make these optimizations more sensible. But if you switch to languages that are additive or like have other properties, do you think they're still going to hold, or would you look into different like?
Yeah, I think that's a very good observation. Basically, all of these are based on the the dataset has different languages, but for this particular, I think the assumption we made here is basically prefix is more important than other parts of the strings, right? So, and I think that is true for English and for many of the structured data, but for other languages, I'm not sure. But yeah, I think that's an interesting question. We probably can like have a strategy to inline prefix or suffix or some of the user-defined way approach.
Thank you.
Yes, I see a question there.
Is it a transparent cache like Fourier and Rust?
Yeah, so we are arrow cache. So a liquid cache is takes in arrow format. So because I think the liquid cache is built on top of data fusion, which use arrow as the memory model, so that every string is input as arrow data, and then we kind of do this like a massage to make the string of our own representation. And when user ask our data, they usually will ask either entire data, so that it will transform into arrow again, but most of the time, user will ask data along with a predicate. For example, they want to say, okay, please find me all the strings begin with HTTPS. So we will do the like a predicate push down, and then we convert the matching string rows into arrow again and return to data fusion.
So the plurality of the strings were categorical. So one could use use application logic and encode those sort of like enums, right? Like use a smaller type and then use application logic. Yeah. Do you have an idea in that data set, how many of those queries required those to actually be strings? Like were they running like expressions that required you to reason about sorting them as strings, or could they have been done in application logic? And I guess the second part is like, should people not even think about that anymore and just let dictionary encoding handle this for you and let the database figure it out?
Yeah, I think that's an interesting trend. Like we usually have a new category called misuse. So basically, we think this column should be some other data type rather than strings. But then we found a lot of use cases. There's different level of engineering happening. Like some people like just want to get the job done, so they just dump everything as strings. And so that can happen. So we see a lot of strings that are true and false. So that's strings. But I guess that works because we have this handling for them. But also we have seen like people using string a more principled way. So they kind of have this deduplication, have this 0 and 1 to represent something in their like application semantic. But I think there's a trend in the string handling that we are seeing people more and more less principled in string handling, because those engines will just handle it for them.
Thank you for affirming my bias that database systems are the most important systems on the planet.
So I think we have time for one last question. Takers?
Can you talk about FSST a little bit more? Any similarities or differences in your compression algorithm?
We basically use FSST for the compressed string here. So we have mixed compression, compressed, uncompressed strings based on the cache hotness, etc. Right. So this are mixed here. For the compressed string bytes, we use FSST. So FSST is essentially take some strings and make it shorter, but preserve the string shape so that you can decode each of the string independent. So for example, if this string points to the uncompressed data, you can directly read it. And if this other strings point to one of the compressor string, you can only decompress this section of the string rather than decompress the entire one and do the selection.
So thanks very much, Xiangpeng. Thanks, everyone.
Okay.
Please give Xiangpeng a hand.
Thank you.